Hi, everyone. Welcome to the very first talk in this academic year for the research seminar that's hosted by the Department of Theoretical Philosophy at the University of Bucharest, Romania. The series of talks is organized by CELFIS. This is the Center for the Logic, Philosophy, and History of Science at the University of Bucharest, and the logistic part and so on is kindly supported via ECUB. This is the research institute at the same university via a project that's funded by First-Order ZFC. I'm very grateful to be the postdoc recipient of that grant. First-Order is the local public funding agency for research, and the code for that project is PN 3 Roman P1 1.1 PD 2019-0535, and we're very grateful to our public sponsor. And having said all that, it's a pleasure and a privilege to introduce our speaker tonight. Michele Friend is a fantastic philosopher and a long-standing friend. It's quite an honor to be able to host her talk tonight. And her talk is titled The Significance of Casting the Relativity Theories in First-Order ZF. Michele is coming from George Washington University and Université de Lille Nord-Europe. Thanks so much, Michele, for being here, and please take it away.
Well, thank you very much. It's a great privilege to be starting this series of talks. And as I was saying to André, I've been to Bucharest, but it was a very long time ago. It was in 1986. Ceausescu was still in power. And I passed through very quickly, and it would have been really delightful to have come to Bucharest again in person. And I've meant to return to Bucharest, but I haven't managed. And I would like to applaud the fact that the University of Bucharest has the foresight to have a center for logic, philosophy, and history of science. I think that this is a very important addition to a university, and to have an institution, or to have that as a sort of separated space from the departments. This can be quite important in terms of doing research. So I think I don't know of very many such research institutions in the world. So thank you very, very much for inviting me, and it is a great honor. So I'm going to talk to you about the significance of casting the relativity theories in first-order Zermelo-Fraenkel set theory. So significance is a philosophical word. When I mean casting, I mean that we're going to write the whole of the relativity theories in a logical language, the language of first-order Zermelo-Fraenkel set theory. And the relativity theories, of course, are both special relativity and general relativity. And I want to talk about why that's important. Oh, hold on, I can't move the slide. How do I move the slide?
You should be able to use the arrows on
the one's down there. Okay, sorry.
No, that's fine, thank you.
Okay, so two elements that I want to bring together in this talk in order to discuss the significance. One of them is the project of the Andéka, Madarász, Németi, Székely, and others. And it's represented in this huge book that was published in 2002. It's 1,300 pages long, if I remember correctly. It's a massive thing. So we sometimes call it the big book. and it reads, I mean, half of the pages are simply mathematical proofs. So it looks like a logic textbook of some sort. And there's a number of philosophical discussions as well that come out in the book, and comparisons of what it is that they're doing with more mainstream science. I want to contrast that project, just use that as one backdrop, and contrast it to the notion of scientific explanations in mathematics, the so-called indispensability arguments. So just use those as two things that are very, very different in the philosophy of science and philosophy of mathematics. And once we've got that contrast going, then we can talk about the significance of purely logical and mathematical explanations in science. And I have a 4-step conclusion at the end. So you can sort of follow along where we are in the talk through those points. Okay, so let's discuss what it is that these people in Hungary have been doing for quite a long time now, nearly 20, well, more than 20 years, because clearly they didn't write the book in 1 year. So to speak to the historians of science, the researchers involved in the logical relativity project follow in the traditions of Poincaré, Hilbert, Axe, Goldblatt, Suppies, and so on. They had it, all of these philosophers and mathematicians had the idea of rewriting a mature science in mathematical terms, because then it would be more accurate, it would be more precise. And they thought that this was sort of the holy grail. This is where you wanted to go if you had a mature science. And the Hungarians that I've been working with, what we call the Andéka-Németi group, they have managed to complete these projects that were started by Poincaré, Hilbert, Axe, and Goldblatt, and Suppies. They never actually finished everything, but the Hungarians have managed to finish it. They have actually extended further than that because they've included Newtonian classical mechanics as well in the theory, and they're looking at thermodynamic theory at the moment. So they cast the relativity theories in the language of Zermelo-Fraenkel's set theory, and they add a few constants because they're trying to describe what happens in outer space. So you're thinking about, and we're just going to talk about special relativity theory here today because it's more complicated in general relativity theory. So in special relativity theory, you only have inertial bodies, that is, bodies that go in straight lines. Photons go in straight lines, these things go in straight lines, and they all go at the same speed. There's no acceleration, so there's no curvature, there's no speeding up, and there's no slowing down. They're just going in their trajectories and whatever speed they're going. So the Hungarians, and we'll see the language in a moment, the Hungarians introduced these constants of bodies, observers, time, trajectory, event, and photon in order to describe all of the phenomena that we find in special relativity. And the point that will be interesting for the contrast that we're going to set up is that they give genuine logico-mathematical, and the reason I say logico-mathematical is some people think of Zermelo-Fraenkel's set theory with some constants as now being a mathematical theory, and some people consider it to be a logical theory. I don't mind, whatever you want to call it, it doesn't matter. But the point is that their explanations are in this very formal language, and they explain, or they believe that they're explaining physical phenomena. And they do this for at least 2 very important theories in physics. So here are some of the axioms. I mean, they're very formal axioms. There are no English words in the axioms, unlike what you find with most physics textbooks. So for example, the first one says that the geometry is Euclidean geometry of n dimensions with field lines, basically straight lines everywhere. The notion of an observer in union with the photons is a subset of the inertial bodies. So you have observers and you have photons, and they're just zooming along however they do in outer space, and they're only going in inertial ways. They're not, again, there's no acceleration. For any h, which is an inertial body, and for any m, which is an observer, the trajectory, so TR means trajectory, of h according to the observer m is a straight line in the geometry. That is, so observers, the whole point about observers is that they're mathematical entities and they can watch a trajectory. For all observers, the trajectory of itself, so what can an observer do? It's going along in this nice straight line. And as you know, when you're at a constant speed, when you're in a train or something, you don't feel that you're going fast, and you watch this landscape going past you. So the only thing that the observer can observe about itself is the time. What time is it? And the time is going at a constant speed, right? It's just going around. So it's these sorts of notions. I won't go through the others because we're not really going to be working with them, but you have a notion of photon. Well, the next one is about the light cone. So observers and any inertial body that's an observer is going inside the light cone, and the photons are going on the outside of the light cone. Axiom 6 talks about the W is your worldview. What is it that you can see? All the things that you can see. And the idea is that the observers can all see each other, and they can see each other's worldviews. So in other words, if I'm sitting in a spaceship going along in this direction, and I see Maria going in a spaceship in some other direction, I can put myself in her place and see what's going on in her world. And the idea of the last one, the axiom E, is Einstein's axiom, and it tells us that the velocity of a photon is always equal to 1 for any observer going in any direction. So these are very basic concepts, and as you'll notice, there's no notion of force, there's no notion of causation. I mean, there'll be arrows when you do a proof or something, but they're not necessarily causal arrows, they're just there. So it's just purely logical. And from these axioms, you can now make deductions, just as you would with any normal set of axioms. And that's what the Hungarians do. So using these and other axioms, so sometimes the Hungarians, they play around and they'll negate an axiom, or they'll add another one. Once or twice, they actually need the axiom of choice for what they're doing. And sometimes they use a non-well-founded set theory to do certain things, just to look at things in another way. So using these or other axioms, the Andéka-Németi group formally derived theorems. The theorems represent the phenomena of relativity theory. The derivations or proofs are what I'll call, for the purposes of this talk, I'll call it the lowest explanations in the theory. We'll come back to this notion a little bit later. So let me just give you an example. So say there are two inertial bodies traveling on different trajectories. One is going up in that direction, the other one's going in that direction, whatever direction means when you're in relativity space-time. And we might know what's the difference in time recorded by the first inertial body with respect to the other inertial bodies. So as I said, I might see that Gabriella is moving in this direction. I say, oh gosh, I wonder what time it is for Gabriella. So I look at my watch and I can observe the watch of Gabriella. And I can observe that Gabriella's watch is moving at a faster rate than my watch because Gabriella's traveling faster. So it's those sorts of phenomena that they can actually capture. They can even capture within this theory something very close to the twin paradox, but they cheat at one point because they have observers sort of jumping trajectories to make the curvature. But they really can capture everything that we want to say in special relativity. And they do the same, then they change the axioms around a little bit, and they do the same for general relativity, and they do the same for Newtonian mechanics. So the place where, and so the proofs are a type of explanation, and the place where the explanation ends at this stage of explanations is with axioms, not with laws from physics. And the axioms are logico-mathematical. The explanation is in the form of a proof in logic or mathematics. As I said, if you look at the big book, you read through the pages, it's just proofs, one after the other, just like you would in a logic textbook. And the notion of the end of an explanation is philosophically important. Why do we want a a notion of explanation? Why do we want an account of explanation in science? It's a little bit to give us a license as a teacher or as a researcher to say, I've explained as much as I need to explain. It's a license to say, stop. You know, the annoying little child that keeps saying, but why, but why, but why? At some point, you're allowed to philosophically say, stop it. And normally in science, you stop it with a law of nature, right? You stop with a Newtonian law, you stop with the law of gravity, and you say, that's the end of it. You can't ask why about the law. And similarly, at this level of explanation, you stop with the axiom. We are using a Euclidean geometry, that's it. Now then you might ask a separate question, which is, do we need to use a Euclidean geometry? Could we use a Riemannian geometry? That becomes the second level of explanation, but we'll talk about that a little bit later. Does anyone have any questions?
I have a couple, but I think I'd better save them for the end.
Okay, all right. All right, so we'll forge ahead, just note them down. All right, so explanation.
Maybe I have one question. The constants that include bodies, observers, among others, do they appear equally in any of the axioms? Yes, right? Or are some axioms that only include some particular constants?
Well, some axioms, no, none of the axioms don't include all of the constants.
Yeah, but what I mean is that it seemed to be that some of the constants relate to particular types of structures, and so there is no difference between them in the axioms. They are equal.
That's right. So they have what they call two types of entities. There's quantities and there's objects, and so the quantities are just measurements, or the number one in this case, and then the other things it's just a trajectory. It's just there. It's a line in the Euclidean space. K is just an observer. It's just an inertial observer, and you find out about K by looking at axiom 2. It's an inertial one. So, and inertial ones have a certain behavior. That is that they are represented as a line in the geometry, and that's it. And then we have a notion of time, so we can get a notion of velocity, and that's what we see in the notion of angle and in the notion of axiom 4. We have time, so they sort of push each other around, these ideas. And you learn about, if I want to learn about photons, then I start to think about the axioms governing photons, and I look at all the proofs that include photons. And that's how I learn what a photon really is.
Thank you, Michelle.
Okay. Okay. So now we're going to shift gear. We're going to move.
Michelle, I apologize if I may. I think we have a hand up from Catalina as well.
Okay.
Yes, sorry to interrupt. So I have a question also regarding the axioms. So are the axioms chosen in a way that they correspond one-to-one, or they assure a complete description of the theory of relativity?
Yes, and they are not necessarily linked one-to-one with laws of special relativity.
But they can derive, starting from the axioms, everything that is actually in the theory of relativity.
Exactly right.
Okay.
And then for general relativity, you need to take some of these axioms away, and you have to, or change some of them, and you have to add a few more because you need acceleration. So, and they have, there's a very beautiful paper, which is a route from special relativity to general relativity. And it's symmetrical, right? You just have to change some of the axioms around, and then you're in the world of general relativity.
This is amazing achievement, actually. If I mean, it looks like they did it, and actually now you can play and prove things and perhaps find some things that were not there. I'm curious to see if this is the case.
That's
Thank
right. Well, I won't talk too much. Well, we can talk about it in the question time, but they found for the exciting new thing that they found was that that a body should travel faster than the speed of light is consistent with the theory. So that means that it gives us the possibility to actually look for those things. You know, at least it's consistent. We don't know if it's true, but we haven't found them because they don't have ways of observing these things, but it's consistent and therefore possible to find if you can work out how to find them. And I have a theory about that too, but I won't go into it. So yes, it's amazing work. It's really incredible work. And we're just going to talk about the tip of the iceberg today, you know, a little bit about these theories. So now we're shifting gears. So we're moving into the world of Quine and Putnam and the so-called indispensability arguments. As you know, Putnam changed his mind several times. So it's just some versions of Putnam. And we think about a sort of Occam's razor principle, and we engage in the famous indispensability arguments, where philosophers are battling over the question whether or not mathematical entities can be removed from scientific explanations altogether. So they want as few mathematical entities as possible, because they feel that the only real mathematical entities are those quantified over in our, or the ones that are left are the ones that are quantified over our best scientific explanations, whatever those are. And it's only those entities that are indispensable to science and therefore real. So real objects are things that you can push and pull and smell and look at and measure and spit on and move. You know, that's the paradigm case of a real object. The number 8 is not a real object, you know, as far as they're concerned, or they'd really rather it not be. Now, if you have to quantify over it in your best scientific explanations, then they will reluctantly agree that maybe we have to consider it to be a real object, but they really would rather not do that. So in this tradition, there's a distrust of mathematical entities because they're not material and they're not causal. It follows that proper explanations in science, and when they talk about science, they tend to talk more about physics than they do about biology or about chemistry, because those have fewer laws in them, and causation is a little bit more messy in those areas of science. But they refer to objects that have mass, extension, or influence on objects with mass, and therefore the objects have or are influenced by the forces, the gravitational force, electromagnetic force, the weak and strong nuclear forces, and if there are more forces that are coming up in science, then those as well. So it's a very different world that they're looking at. It's not this septic, logical, mathematical world. It's one of pushes and pulls and forces that are influencing things. So explanations now end with causal laws that govern entities with a force. And that's when the annoying student or the annoying child who keeps saying, but why, but why, but why, you say, that's a law. It's a law of science. I get to stop explaining now. So it's an interesting way of thinking about explanations, which is a little bit unusual, I think, in the philosophical literature. So the thinking goes, mathematical entities have no mass or extension and therefore cannot cause, right? They cannot really be objects because they don't cause real objects to move. And mathematical entities such as numbers, angles, shapes, they're sort of ethereal. There's something spooky about them. There's something a bit odd about them. There's something we distrust about them. So one way to see the puzzle is to remember that grammatically, we treat mathematical entities as objects. That is, grammatically in the sense that we quantify over them. So the grammar doesn't make a distinction between the tree and the number 8, right? It's still the tree and it's still the number 8. If I say all trees and I say all fields within the geometry, then I've used the quantifier all, and the grammar doesn't make a distinction. So the language deceives us about what counts as explanations because it can't differentiate between those two things. The math looks the same. The grammar in English or in Romanian, in Spanish, all look the same. So we're sort of a little bit deceived by grammar, and then we have to do some metaphysics in order to work out what to do about that. So, and in the debate, in this tradition, we have sort of degrees of acceptance of mathematical entities, and there are two separate poles. One of them is to get rid of as many entities as possible, and the other one is to claw back and get as many entities back into science as possible. So some of them are saying, no, here's a way of eliminating this from this particular, and they tend to focus on one explanation at a time, right? So they'll be explaining things like why it is that cicadas, a certain type of cicada comes out on prime numbered years. So there's one little host of cicadas that comes out every 13 years and another one that comes out every 17 years. And the explanation for why this is optimal is that they won't meet each other. They aren't going to compete for food except every 450 years, something like that. I don't remember the numbers, but and that's supposed to be an explanation in biology about why it is that prime, and the notion of prime number seems to be indispensable to that argument. So then we claw back from the people who want to get rid of the mathematical entities, we get at least our prime numbers, and we probably get the other numbers as well. So that's one, and so the debate will be, hold on, is there a way that we can eliminate this and still have a good scientific explanation? And then there's a big debate about what counts as a good scientific explanation and so on. So this is one tradition. So now notice a tension between the project of the Andéka-Németi group, so I'll call it AN, and this Quine-Putnam, whoops, CUNY, sorry, bad spelling mistake up there, Quine-Putnam QP debate in the philosophy of science. So with the Andéka-Németi group, they trust mathematical objects or logical properties, and they trust formal language. In their science, there are no forces. Even when they do general relativity and you have curvature, what you have is just curvature. It's just a turned line. It's not a force. It becomes a sort of a curved line in the Euclidean plane, or they use a Riemannian geometry. There's no causation. And there's going to be a next stage in the explanation, as I already hinted a little bit earlier. In contrast to that, so I'm just putting up this contrast group so that we can ask some questions about significance. So in the Quine-Putnam group, the trusted objects are physical, and formal expression is just a device to make sure that we are precise and that we can make calculations. There are forces, they are causal, and there's no next stage of explanation. So explanations end with citing a law. So explanations, now I'm going to retract and be a little bit more philosophical. Explanations in science are an act of communication. The more basic sorry, I can't actually see that part of, oh, here we go. The more basic the concepts, the more immediate they are. A logical axiom is an immediate judgment, not in the sense of time. So Anglophones, I don't know if non-Anglophones get confused about this, but Anglophones think of immediate judgment as being a snap judgment that is immediate in time, but it doesn't mean that in logic. It means that it is non-mediated. It's an end judgment. It's a basic judgment. It is so basic that there's nothing more that you can say about it. So it's something like a law of logic or an inference rule, in the sense that it cannot be further justified by recourse to that scientific or mathematical theory. So it can't be further justified by recourse to the scientific or mathematical theory. That doesn't mean it can't be justified at all. It can be justified in another way. So if we require further justification, then there will be it will come in another form, right? It's not now going to be a proof. It's going to be either by looking at another mathematical theory or by reference to philosophical considerations and arguments. And this would be a sort of second stage of explanation. There's actually a third one, but I won't discuss it during this talk. Actually, I do. I think I discuss it a little bit later. So a mathematical pluralist, so any of you who know me well know that I'm a mathematical pluralist, they believe that there are several foundations for mathematics and that each brings a perspective and a way of seeing most of mathematics, or most of the rest of mathematics. So other foundations are things like type theory, non-well-founded set theories, the different extensions of Zermelo-Fraenkel's set theory. So ZFC is another foundation. Sometimes model theory can be separated out from that. So there are several of these foundations, and each is just a way of seeing the rest of mathematics, because you can reduce mathematics to that theory. Nevertheless, the Andéka-Németi group chose Zermelo-Fraenkel set theory because it is central to mathematics for a community of logicians and mathematicians, but not because it's foundational. So by central, I mean that it's a lingua franca, or a reference point. For this community, they find it reassuring when they can reduce their theory to this area of mathematics, or their area of mathematics, sorry, to ZF, or they compare it to ZF by means of an equiconsistency proof, or they indicate that what is added or subtracted from ZF to develop their theory. So it's really a very, very strong centralizing reference point. And this is where they feel comfortable. This is when they feel reassured that their explanations, their view of science is in the best form possible. This is the maturity of the science for Hilbert. This sort of confirmation gives the theory a sense of objectivity and robustness. And I'm going to give you two different notions of objectivity and robustness. One of them is because the theory exercises what we call cognitive command. I take this from Wright's book, Truth and Objectivity, which he published in 1992. That is, it's not a subjective or individual matter whether 3 is a subset of 8. We prove this, and proofs are public displays of reasoning that can be checked and can be verified and can be argued over. Logic commands our reasoning. So when you go through a proof and you follow the logical rules, you can't deviate. It sort of locks you into this reasoning. There are different ways you could go in a proof, but once you've decided what your next, so for example, if you have A and B, you can conclude A, or you could conclude B. So there are two ways to go. But once you've concluded A, it follows logically from A and B, and therefore, and there's nothing to question. So this makes, and it's in this sense, the sense of the logical must that commands our reasoning. And this makes ZF internally robust and objective. That is, each theorem follows from the axioms, logically follows from the axioms. So part of the significance is the enjoyed internal objectivity brought by proofs subjected to public scrutiny. Are there any questions? So, well, maybe I should just do the next slide first, and then I'll ask for questions. Now, the equiconsistency proofs of ZF with other mathematical theories is significant because it means that we can check the proofs from the basis of other mathematical theories. So we could move into an extension of ZF, or we could go into a certain core of ZF, or we could go into type theory, which has been proved to be equiconsistent with ZF set theory, or a non-well foundation set theory. since to make an equiconsistency proof, we require translation between the theories. So you just follow that translation, and then you work within that theory, and you see the same phenomena, the same similar looking proofs, but we do that from a different point of view. And these checks are also types of explanation. These are second level, what I want to call for this talk, second level explanations. They're reconceptualizations. So we rethink what it is that we're looking at. When we can perceive the same object or theory from different angles through the lens of different theories, we have another type of external objectivity, what Wright calls wide cosmological role. That is when you see the same thing popping up from very different discourses, from different ways of seeing things. So the same information is true in several different mathematical theories. And then we can think of them as sort of meta fixed points between the theories. They're kind of attractors, if you like, is another way of thinking about it. So you have these two very interesting conceptions of objectivity. It's not the concept of objectivity that we find in the Quine-Putnam indispensability arguments, where objectivity is reduced to a physical object that you can push, pull, spit on, smell, move. It's instead a more maybe philosophical sense of objectivity. Okay, let's see where I go from here. So now before I move on to the conclusions, maybe let's see if there's someone else, if anyone has a question.
Plenty of questions, but later on.
Okay, I can just forge through the conclusions then. So the philosophical literature on the topic of mathematical explanations for physical phenomena has not yet engaged the logical relativity theory project, even though both things have been around for quite a while now. The contributors to the debate rest content with isolated scientific phenomena, so they'll look at one explanation at a time, in which the mathematics in the explanation seems to be dispensable or indispensable. So I gave you the example of the cicadas, and then the debate will be over whether or not the notion of prime number is actually part of the explanation, or whether or not it's indispensable or dispensable for the explanation. So again, that's just looking at one phenomenon within science. But said literature should engage this project because Andréka, Madarász, Németi, Székely give a purely mathematical explanation for whole physical theories, not just isolated phenomena. So that's one conclusion. There's a quantifier difference in the questions that drive the concept of explanation. So this is now a philosophical point. So for Quine and Putnam, we might ask, do there exist, existential quantifier, mathematical entities that are indispensable? So we might use the necessity symbol. For this, there is a unique or a constant scientific explanation. In contrast, we would say with the Andéka-Németi group, can we completely represent all of the physical phenomena of the scientific theory without, that's a negated existential, without forces, causes, mass, extension, and even physical objects? Because the objects, the observers and the photons, they don't have extension. They don't have mass. Events are simply, events are characterized as the meeting of two objects in the same place in the Euclidean geometry. The epistemological significance is that the conceptual resource provided by Zermelo-Fraenkel set theory concern the sorts of questions being asked by philosophers about explanations. Where do explanations end? And this is a nice philosophical question. It's one that, as I said, the philosophers don't tend to put things quite in those terms. And how are they ultimately justified? What justifies an explanation? And that's the question about when are you allowed to stop with your explanations? Do you stop by citing laws, governing forces, that cause movement or cause events, or by first order logic and mathematics. And then you might say, well, which is the better explanation? Why is it better? And we saw a little bit earlier on why it is that one might have a preference for one over the other. And these might just be cultural differences. They might be deeper differences, I'm not sure. Third point in the conclusion, there's only four. We raise the point about objectivity in science or of quality of explanation by looking at this contrast. Logic and mathematical proofs, or logical and mathematical proofs, are both internally and externally objective in the sense of being derivations within a robust mathematical theory, and in the sense of being verifiable in other robust theories. Robust means equiconsistent with. So they are ones that that can be verified in another area. And the last point in the conclusion is that a third epistemological significance is that with the interconnection of Zermelo-Fraenkel set theory to other mathematical theories, we're invited to explore the same phenomena from different mathematical points of view. I think I've got a fifth one. Yeah, and it gets actually much worse. So it gets worse because the Hungarians, when they're trying to understand phenomena, they will also look at when it is that the phenomena starts to break down. And when I say when it is, that's when we change the mathematical parameters. So they're really looking at the edge of the theory and the edge of the phenomena, and when does it stop working? And it's looking at it from that it's no longer working point of view that they start to feel that they can understand better what is happening. Karl Popper, a very good philosopher of science, told us that there are three levels of explanation. When you get the nice warm feeling, which is when you're in the classroom and you think you understand, and then you go home and you have no idea what happened. The next one is when you can explain it, which is what you have to do in a test, or explain it back to the teacher. And the third one is when you can refute it. That's when you get your PhD, right? And that's when you know where the edge of the theory is. And it's that completeness that the Hungarians have been after. So for this reason, the tool for reasoning, that is Zermelo-Fraenkel set theory, this reaches further than the mathematical theory itself. And as scientists, using this tool, it invites an interplay between logic and philosophy. And we only develop our understanding of the relativity theories by extending our explanations and justification, not only in the direction of mathematics and logic, as well as science. You know, I'm not saying that we should stop making observations in science, but we use those observations and we find out how to express them in a formal theory as well. So once we've done that, then we're led into the direction of mathematics, we're led into the direction of logic, and we're led into the direction of philosophy. We're asked to ask very philosophical questions. So in this way, in this type of project, we have logic, philosophy, and science working together. So I'll end there, and thank you very much for your attention. It's been a privilege, and I hope that there are some questions.
Thank you so much, Professor Friend. And I'm going to use this digital applause button, and I see that the others in attendance have already used it. We very much appreciate your talk, and I'm going to stop talking right now, and I'm going to give way to our colleagues for questions. And,
well, maybe you should choose them. So yes. I think that Friedrich had a question.
Oh, did you, Friedrich? We might get to him in a second. I see Maria has her hand up. Friedrich, if you have a question, please do signal that.
Yes, if I may. Thank you. Okay. Thank you for this wonderful presentation. I have 2 points, 2 more general points I would like to mention, and perhaps you would comment shortly on this. First point, there are discussions of the question of ontological commitment of a physical theory, where the Quine position is changed to a moderate mixed view. There's, for example, Catland, who speaks of mixed objects, objects mixed of mathematical and physical entities, especially the measurements. I myself have a paper on truth makers for first order logic, where I have another proposal for deviation. That's one point. Would you think the opposition to old-fashioned on what there is ontological commitment is today really an option to discuss? The second point is I appreciate this presentation in ZF. I like ZF, as far as I know it, of course. Abraham Frankl Parallel was a wonderful book to read. Okay, I think why not see it as a complementary? It's I have one way to develop a physical theory in ZF, straight down, top down from axioms, and I have another way which is loaded with physical understanding by analogies, because we have of any physical object, we have to ask, is a physical object in the sense of this theory, is it what its name says with a physical object? It's a measured quantity, but what is an object? Okay, so my one question was about ontological commitment. Do I need a discussion on what there is? And the second, why not see it complementary, except the Putnam-Quine view as transporting what physicists think or want to express or see in their laws, but knowing that there's much of analogy, that there's much of non-observable objects by analogy to observable objects. Okay, and so I think there need not be a contradiction, but a complementary situation. Thank you.
Yeah. Well, it depends on what you think ontological commitment means, whether or not the conflict is real or not. But I'm very much a fan of mixed objects, and going back to Meinong and talking about things that so exist. And I feel personally I'm not very comfortable with talking too much about ontology, because it's for me it's a fairly confused area. I'm more comfortable talking about objectivity than ontology, and so there's in the more traditional philosophies, your ontological commitment had to be tied to having an object, and then what was an object, and you're shaking your head because I think that we agree that this is not necessarily the way to go. And you can have truth without ontology, and you can have ontology without, with anti-realist truth. So, right. The philosophical space is actually quite diverse, and it's for that reason that I'm not as, yes, I love mixed objects, and there's all sorts of, like the equator. The equator doesn't have any mass; it has a location. It's a sort of mathematical object, but stuff happens. You move from one side of the equator to the other, and the water goes down the hole the other way. So it has a sort of weird causal influence, and it's just a location. So well, it isn't, because there's a magnetic, there's an explanation for this. But so I think that we agree. And yes, I would very much like and I'm aware that the debate has moved on, and I wasn't addressing the more sophisticated versions of the debate. I'm not sure if I've answered your second question.
Excuse me, if we could have a complementary view of the Quine-Putnam and the ZF.
Yes, yes, I think we can. I mean, we can as long as we don't get too worried about this notion of ontological commitment. And for me, the different points of view are simply enriching each other. You know, as the Hungarians do, when they move into another mathematical theory, or they change the mathematical theory by changing the axioms, they're looking at things from a different point of view. And I'm quite happy to, you know, put on the hat of Quine-Putnam and saying the only objects that I'm going to see as an academic exercise, how many mathematical objects I can take out of my explanation. And then I'll ask the very important question, what counts as a mathematical object? And what do we do with the mixed ones? So, and these are very good questions to ask. They're lovely ones. But for me, that will be an academic exercise. And similarly, if I want to do the whole theory in a mathematical logical language, this is a way of doing things. And it doesn't, and the Hungarians are very adamant that they're not saying that this is the way to go. This isn't what we should be doing. They see their approach and their way of doing the science as being complementary to the more laboratory-based, observation-based, more intuitive way of doing science. So yes, these are different perspectives, and the more the better.
Thank you.
All right, thanks so much to Friedrich. And next up we have Magia. Thanks so much for your patience. Please go ahead.
Thank you, Michelle. So during the talk, you mentioned at least three types of justification. So the first one is epistemological, and it can be illustrated when justifying an explanation in laws of nature. The second type of justification is, in a sense, inferential or semantics related, which is going to be justifying a theorem in an axiom. And the last one is going to be like a type of linguistic justification, which is going to ground our uses or our understanding of what is being said in a more clear or better accepted language. So what I was wondering is whether the status of explanation in the sense of being justifying or being justified in an epistemological sense can be, how to say, transitive through the different formal languages that we are using to analyze a particular theory. Because what I can say is, if I am a skeptic about the scope of these explanations, is that what you are getting here through set F, through a set of representation, is only an explanation at best of the theory, of the formal theory of general relativity or the relativity theory, but not the theory in itself. So that's the reason why the explanation, it's not going to hit the empirical world. It's not going to be about that. So the elements that are going to be involved in the set of explanation are going to be elements that relate to axioms, inference relations, maybe the semantics, maybe the logic that is underlying, but not necessarily anything about the world. And so when you compare these two things, maybe the justification that is actually transitive is the linguistic one, or maybe the epistemic one, in the sense that I get a clearer idea of what's happening, and obviously the semantic one, but not necessarily the one that we are trying to figure it out is if it is there. If there are mathematical explanations of empirical elements, and this is a case of that. So do you have any thoughts on that?
So you mentioned at one point the very interesting notion of transitivity between the explanations, if I've got that correct, or transitivity of the justifications for explanations, is that right?
Yes, yes.
I don't think that they are necessarily transitive. I mean, I don't know. I don't know. I would have to think about that. So what counts as, I mean, I think what you're asking about is what counts as a justification for an explanation, or what should be counted. And as you pointed out, there are different types of justification for an explanation, and they belong sort of to different mindsets or different schools or different ways of different sort of meta-philosophical positions, where the priorities are. And they are, I didn't say too much about the linguistic element, except to talk about a formal language. But of course, they're very language sensitive. And as soon as we make a translation from one theory to another or one language to another, there are things that we lose and there are things that we gain. And that's why I'm not sure about straight transitivity.
After the next question, may I have a follow-up on this? Thank you.
Please, yeah.
You may naturally. I was wondering if you'd like to have it now.
No. It is fine to move to the next one, and then in a second round I can ask.
Okay.
Thank you, Michelle.
With Catalin's permission, I kindly inserted myself in the queue, so I'll ask a first question now, and then I'll save the worst for later. So one thing, this might be a follow-up to part of what Friedrich was saying and part of what Maria was saying. One thing I wasn't sure about is exactly how the pieces of the puzzle fit together. So if, for instance, we think of the Quine-Putnam tradition, it would seem that the indispensability arguments at play went through a few stages, as you also mentioned. And the first stage is, if you like, Mark Collivan's book in the 2000s epitomizes this in a way, sort of focuses on the ontology of it. In some sense, we couldn't do Newtonian mechanics without a calculus or something of the sort. Or we couldn't figure out the cycles of cicada multiplication if we didn't have a theory of prime numbers. So that seems to focus more on ontology, right? But then this sort of seeped into philosophy of explanation with Alan Baker and people who want to point out that there might be an explanatorily independent role for bits of mathematics to play within various physical theories. And there seems to be room for distinguishing explanatory indispensability from, say, purely metaphysical accounts of indispensability or something like that. At any rate, it seems to me that this tradition, talking about the indispensability of various bits of mathematics to physical science, sort of evolved throughout time. And it wasn't immediately obvious to me exactly what bearing this had for explanation in general, especially since you later went on to sketch some fantastic notions of objectivity from Kristen Wright. And so these seem to be, in some sense, well, I wouldn't say non-committal metaphysically, but their commitments seem to be somewhat leaner, right? And so I wondered, was the ontology business a separate piece of the puzzle, or did you mean to focus on the interplay between the indispensability and the explanatory aspects of it? Or so, yeah, that's.
Yeah, it was an exercise in setting up a contrast group so that we could see a little bit more vividly, you know, by comparing to something quite different. So it was just, I mean, I could have given a talk simply on what's going on with the Andéka-Németi group, but then you wouldn't have seen why that's important. You know, so it's important if you are, it's sort of really weird looking if you belong to a certain type of tradition. It's not weird looking if you're a nice, fresh student who hasn't been, seeped in philosophical traditions yet, and you might think it's a little bit weird to do this, but
it didn't seem weird. It seemed wonderful. But I'm going to turn my second question into a quick follow-up to this, because at some point you mentioned you're a pluralist about alternative axiomatizations of set theory. And each of these is in some sense a different view of the same terrain or something like that. And well, whether it's the same terrain or not is up for grabs. But why not? That seems to go very well hand in hand with an explanatory pluralism, right? And if so, the question is, well, why focus on this tradition or that tradition? Or why not just be pluralistic about it all? And then put the burden of proof on the Andéka-Németi group and say, well, why would we need to entertain their kind of explanation instead of being pluralistic?
Okay. Yes, I didn't want to bring the audience that far. I was trying to be nice, but yes, I mean, yeah, then you can explode and you can, yes, become very, very pluralistic on a lot of different levels. So it's an invitation to do that. The Hungarians are very pluralistic as well. So they say, look, this is, I mean, if you have, when we have these very honest moments and they will say, look, this is the tradition that we feel comfortable in. Doesn't mean you will feel comfortable in it. And we invite you to develop your own way of doing things. They had very interesting exchanges with someone called Thomas Benda, who has been, and there's some Brazilians as well who have been working on using Gödel-Benay's set theory to do the same sort of, I mean, the Brazilians are doing quantum theory instead. So it's different physical theories. And Thomas Benda was doing the relativity theories using Gödel-Benay. He didn't get as far as the Hungarians got, but they're very happy that this is being done. So they are pluralist, but as a scientist and as a researcher, you have to start somewhere. You start with what it is that you do know and you feel familiar with and you like. And, as and when you have the time, I mean, if they could live forever, then they would also look at it from a Gödel-Benay's point of view, et cetera, et cetera. I mean, they don't mind at all. It's just, and the reason for Zermelo-Fraenkel set theory is, I think it's fairly political, that it's well accepted within certain traditions, et cetera. Had they started with Axel's non-well-founded set theory, even though now we know that it's actually equivalent to ZF, and there's ways of translating they're fairly loyal. At the time, it would have been a little bit weird to do. And then even fewer people would have looked at the work. So it's really for those sorts of reasons, but they're very happy to, you're right, that the notion, and you're right, that Wright's conception of objectivity is exactly not grounded in an ontology, which a little bit follows Friedrich's concern too, right? That we want to, the notion of ontology is a bit, we need to re-examine that very carefully now in philosophy. We can't rest content with push and pull and kick and move. That's, we have to really leave that behind and think more, return to Meinong and the medievals. The medievals were incredibly sophisticated, and we've forgotten. They have all these lovely subtleties about chimeras and about hallucinations and about things that appear to you because some spirit sent it to you, a devil or something. And these are different because they have different reasons, different origins, and how do you treat them and how do you reason over them? So there's a lot of subtleties that we've forgotten, that if we want to have a good, thorough account, we should maybe revisit some of them. Anyway, it's great fun reading the medievals.
Yeah, and thank you so much. And I couldn't agree more. The due reappreciation of lost and found medieval traditions or other metaphysical traditions is more than welcome. And I hope that can only flourish. Thanks so much, Michele, and I'll probably come back with more questions, but I want to give way first to Cătălin and then to Maria's follow-up. Cătălin, please go ahead.
Thank you, Andrei. So, Michele, I have a question regarding your second and third conclusion. And the base of the question is the following. So I totally agree with point 3, for example, that the logical mathematical approach is much more objective, and it's much easier to play with a mathematical construction based on Zermelo-Fraenkel and to see how everything goes from axioms and so on, right? But then comes to point number 2. What do you think, and this is the question, so what do you think about the fact that actually the way scientific theories are done is not like this, right? So it's not like Andéka-Németi came up with this book and showed the theory of relativity. It's actually Einstein who proposed it, and it was based on the law of physics, right? And it looks like it goes like this. And it looks like the Andéka-Németi approach is very good in extending and maybe testing more the initial theory than actually starting using it as a starting point.
Yes, very good. So I had some very good exchanges with Giambattista Formica, who's a specialist in Hilbert, and we wrote a paper together exactly on this point, that Hilbert's view, I mean, under Formica's reading of Hilbert's view was, once a science becomes mature enough, it can then be expressed more and more and more mathematically, more and more precisely. And so it's really the cherry at the top of the cake. It's only appropriate with a very mature science and not before. So you're right, when Einstein was coming up with the relativity theories, we couldn't have started with the Andréka-Németi project. We have to end, I mean, it's an infinite project, because once you decide, oh, now I can hop to another mathematical theory and look at the same phenomena, and I can see where it starts to break down and where are the edges, and then I can reconstruct it, adding another dimension. Yeah, so you have an infinite amount of mathematical play, but it takes a maturity in the science before that Andréka-Németi type project, or the Suppies, Goldblatt, Axe, etc., that aspect can actually be engaged in. So thank you for the question. Yes.
Thank you.
Thanks so much, Cătălin and Michele, for answering. Maria, please go ahead.
Yes. So let me try to rephrase where we were. I was wondering whether this epistemic explanatory role that we associate, the epistemic role that we associate to explanations, is going to be transitive from these types of representations to the actual domain that we want to be explaining, right? So what part of the discussion about Quine's worry about logic and its relations, logic mathematics and the relations with science, was whether logic is a good and mathematics are good, and particular mathematical theories are good elements to represent particular phenomena in the actual world, and if they are legitimately good at doing so. And so one of the main concerns that we might have is that set F is not, because it is a mathematical theory that is usually used to represent that if we assume that it has a particular domain of application, that it's privileged, it's not going to be the empirical world that the physical theories are talking about. But we have these discussions about the applicability of mathematics in empirical sciences, about other types of or other particular mathematical theories. So the question is, okay, we can represent what general relativity and especially its mathematics says in set theoretic language, but does it mean actually something? The explanations that we get from these set theoretic representations, do they actually refer or in a sense include the explanations that, or even ground the explanations that we have about the empirical world in this other mathematical theory? And so,
okay, let me try to answer that. So I mean, the Hungarians will claim that what they have done is recovered all of the phenomena that we find in the theory. And they claim that they understand the theory now. And they did, so it's very interesting. They say that they did not, because you're interested in the notion of understanding as well. So they claim that when they were studying physics, they would ask things of their teacher, for example, to explain the twin paradox, because they said, sorry, I don't understand it. It's too strange. And the teacher would say, and Hungarians have a very, very strong tradition in science. And the teacher would say, well, at the end of the day, you sort of get used to the explanation. You sort of internalize it in your body. It becomes a sort of gut reaction or something. And the way that they described that is that they said, well, you know, if you take courses in relativity theory, and if you write a PhD in relativity theory, and if you start teaching relativity theory, you might feel that you have now understood what is going on with the twin paradox. And they said that's not good enough. So for them, they thought that they could not understand it. They could not understand. So what is it that we're trying to describe? We're trying to describe the results of experiments, right? We're trying to describe the phenomena of, you know, the fact that if you stand, I mean, you can even, I mean, your GPS system, for example, it wouldn't work if you use Newtonian mechanics. If you didn't have relativity theory, the GPS would tell you that your car is located somewhere in Bucharest. And that's not useful. You really need to know that the satellite is really far away and that there's not very much gravitational pull, and it's moving at a fairly high speed, by the way. So unless you make all those calculations and you get the relativity thing going, it's not very accurate. But to understand why it is that these things are different, you know, why it is that you need to have, why it is that it's significant that the satellite for the GPS is way, way, way above the Earth, and that it takes time for the signal to come down, and blah, all the other stuff that you need. To understand that, the Hungarians feel that they need to do the math. Now, other scientists might not feel that because they've internalized it. They've got the gut reactions. I remember when I was studying Newtonian mechanics, I understood what a lever was. You know, I understood you put it on a little pedestal and it's really long. And if you step on it like this, then the thing will go up. I internalized that because that was the end of the explanation. We weren't given a logical explanation, thank goodness, at that stage, right? You know, I don't know, 16-year-old sort of sitting there in front of Zermelo-Fraenkel set theory, it wouldn't have worked very well. But so you're asked to internalize. And the students who can't internalize, they're basically told, well, maybe you shouldn't do physics. Right? So there are those two different, if you like, two different traditions in. So, I mean, one of the very deep questions that you're asking as well is, what is the phenomenon? How can we even recognize what is the phenomena that we're trying to describe? Does it have to have force and causation and be physical? Is the right analogy? So I think it was Katalin who mentioned the notion of analogy in our reasoning. Science is all about analogy, and the mathematics is analogous, right? It's an analogy type of reasoning. The inertial bodies refer not to actual bodies, they're just mathematical entities. And when an so-called observer makes an observation, the observer makes a measurement, and it's a purely mathematical act. It's not a physical act. They don't take out a ruler. They don't look at an actual, an actual clock or an actual watch. It's a purely mathematical act, a registration of a number. and we have the experimental data to tell us about the phenomena that says, you know, by the way, if there's an eclipse of the sun, we can observe through the Michelson-Morley experiments, we can observe the curvature of the light, okay, or something. We can observe something. And one explanation is that the light itself is actually curving around the gravitational pull. Another one is that space-time is curved, you know, so there's alternative explanations. And the phenomena, you're quite right, the phenomena comes from the observations. It comes from observing what we take to be. But then it's what are we taking them to be? We're taking them to be sort of physical objects that we can bump into. And the analogy is that, oh, you know, we're thinking in terms of spaceships, and we're thinking in terms of straight lines, and we're thinking in terms of, and then a photon is just a weird thing because it goes really, really fast and it can't see anything. It can't even observe something. So it's a very odd thing. And so I can't pretend to be a photon. I can kind of pretend to be an observer. So what is it that we're understanding? What are the analogies that we accept? And how can, I mean, it's a very nice question. How can completely dry mathematics that, as you said, is not intended to do physics, suddenly start to use it to do physics? And that's where Hilbert comes in. That was what Hilbert thought under Formica's reading of Hilbert, and not a very formalist reading of Hilbert. But if you go back into Hilbert's notions of science and what he thought about science, there is a reading where in the mature science, it becomes more and more and more mathematical. It becomes drier in that sense. It becomes much more a calculation. And it's probably a really, as I sort of hinted before, it's probably a really, really bad way of explaining things to beginning students. So it would be a disaster to show them the Andéka-Németi book, you know, and say, oh, we're going to work through this, you know, now that you're 16 or 17 and you want to learn about science, this would be disastrous. So it's not for learning. What are these explanations? These are sort of a type of, it's a mathematical logical explanation. It's a kind of ultimate explanation. But the objectivity, if you're somebody who thinks of objectivity as having to be tied to an object, and an object is something with extension and mass and laws governing it, and that's the analogy that you have with objects, then you're going to not accept these explanations at all. And you're going to say it's not describing anything that I recognize. So, let me give another analogy since André brought up Frege at one point. So Frege criticizes, I think his name is, you'll have to get me right, but the Steiner or someone who said that mathematics is simply the muscles moving in the brain. Okay, there aren't any muscles in the brain, but it doesn't matter. But it was kind of movements in the brain, all right? And Frege says, I don't recognize mathematics in this. And similarly, you might say as a physicist, when you present them a whole bunch of proofs in Zermelo-Fraenkel set theory, they'll say, I don't recognize the phenomena in this. First of all, I can't read it properly. Secondly, you know, I don't see the law of gravity anywhere here. I don't see F equals ma. I don't see, you know, you've got Einstein's thing, and so we've got the light cones, but I don't see what we're talking about. And so there is a question of language there, and there's a question of what we're used to. And there's a question of, the very nice question to ask is not only where do explanations end, but what are they for, or who are they for? So there are for people in different communities. And so explanations, in some sense, they also end phenomenologically when you get that nice warm feeling. And then at some point you go, oh, well, I've lost the warm feeling, so I need something better, right? So, or you need to go over it again. So So these are the best philosophical questions, and those are the ones I wanted to raise, not solve in today's talk. So I'm very glad about the questions that have surfaced, because they are going to the very core of what we want in science, and what we want in philosophy of science, and what we want in logic.
Thank you, Michele.
Okay.
And that is such a happy note. That is fantastic. Thank you so much. I have lots more questions to ask, but I'm going to wait for them to sediment a bit before just producing them out loud. Because I'm happy that you're happy that these questions sort of came up, and so thanks so much, Michele. This has been a beautiful talk. I'm delighted that this is the first talk in this academic year that our department is organizing. Thanks so much to Maria, to Katalin, to Friedrich, to everybody in attendance, and we wish you well. Stay safe, stay healthy, and I hope to see you very, very soon in person. Thanks.
That would be very nice. I mean, if you want, so are we sort of stopping?